So we are going to just begin analysis through what is called sequences. So let's see. So uh, we shall embark on understanding real numbers via the theory of sequences. Okay. So I'm basically following Terry Tao's book. Let me comment it in elsewhere as to why I'm choosing this book. But so we are trying to at least what Terry Tao is doing is he has a chapter on understanding real numbers, and to do that he wants to see that every real number could be seen as a uh, this this have to be made precise limit of a sequence of rationals. So anyway, so let's get the technicalities as we go along. So sequence, if you see, you would have seen uh, the word sequence uttered in various contexts, and probably even when you look at things like an arithmetic progression or a geometric progression, etc. These are the things you would have seen in school. So, to be very precise mathematically, let me consider a function f whose domain is natural numbers and codomain is real numbers. So, we are interested in sequence of real numbers, infinite sequence. In fact, yeah, this is the more general one. We can even consider finite sequences. We are interested in infinite sequences of real numbers. I guess I should make it a little lighter. Okay, so a function of this sort uh, actually depicts a sequence, because we generally think of a sequence like this. Xn is something like x1, x2, x3. This is what I've depicted in the class. So if you want to know this, if I set f of 1 as x1, f of 2 as x2, and so on. So the range of that function f is precisely a sequence. That is what we mean. So we can always consider a function from natural numbers to real numbers to depict any sequence. That is the point I want to uh, emphasize when you want to define a function, define a sequence. Now, with this, let me give examples here. For example, if I look at the sequence of natural numbers, just very trivially, 1, 2, 3 itself. This is nothing but the identity function uh, like this. F of 1 is 1, f of 2 is 2, and so on. That is, f of n is equal to n for all n belongs to n. This generates, let me give a name, xn is, let's say, this sequence. This generates xn, right? Let's say, I will say let yn. I think there's an issue with my microphone. Yes. So I think now it's audible. So till now, what I said is that a sequence can be mathematically defined as a function f from n to r, because whenever you have, let's say, x1, x2, etc. as a sequence, you can simply set that f of 1 equal to x1, f of 2 equal to x2, and so on. So, as you see here, it's an infinite set parameterized by natural numbers. So if you set your uh, image of 1 as x1, image of 2 as x2, and so on, you automatically realize this set. Therefore, I just now gave the identity function fn equal to n, and that generates your, let's say, the sequence xn equal to the natural numbers sequence. This is generated by this function. Let's take another thing. For example, your constant sequence 1, 1, 1, or more generally, k, k, k. Let me give this name as yn. So how is yn generated? You can generate yn as by the function f of f n to r as f of n equal to k for all n belongs to it. So we generated another example, which is standard in books, called as the constant sequence. And then let's take another sequence. Let's say I want to generate 1, 5, 9, etc. You already see this as an arithmetic progression with a equal to 1, d equal to 4. That is, your progression, your sequence is given as a plus n minus 1d. Set your n equal to 1, you realize 1, that's a. Set your n equal to 2, you realize 5, and so on. And therefore, this is your AP sequence. So f of n equal to a plus n minus 1d, which is same as 1 plus n minus 1, 4. So this generates your AP. So as I began saying that your prior knowledge about arithmetic progressions and others, for example, the GP, the geometric progression, HP, the harmonic progression, etc., all of them could be uh, understood in the from the theory of sequences. Okay, so having said that, let me come down to some technicalities. So there is this concept of convergence, and for this, without okay, my goal here is to look at all these things without much uh, technicality, etc. So, but with your school 11th, 12th understanding of limits, etc., you can look at. So I've defined sequences functions. So if you look at limit of this function f as n tends to infinity, and this is a finite real number, if that is true, if such a definite limit exists. And by what I mean by definite limit, it has to be a finite real number. Remember, I am in the context of infinite real numbered sequences. So therefore, I do expect L to be a finite real number. Then so what okay, so this the argument is n. So if If this limit exists, then it's called convergence. So so what are the other possibilities? Even before going to the let's take some examples. So we will eventually see that the kind of examples I gave, the constant sequence and the AP, etc. Among them, the constant sequence, I would say, because I would make it arbitrary, Fn equal to K is convergent. And why is it that so? Because limit of such an F, I should not write it in that way. This is the right way, is equal to K, and K being a real constant, and therefore it satisfies our definition. Okay. Whereas if you look at, let Fn equal to 1 plus n minus 1, 4, which was your AP, AP, that is 1, 5, 9, etc. If this sequence has to be seen, you see, even if you intuitively look at the plot of these points, it is eventually going to infinity. It's going to grow to infinity. So intuitively also, I see that there is something wrong happening here. So limit of Fn as n tends to infinity is limit of 1 plus n minus 1 to 4 as n tends to infinity, which is limit of this function 1 plus 4n minus 4 as n tends to infinity is clearly infinity, because this expression turns to be something like 4n minus 3, and that goes to plus infinity. So now it's the time to look at some kind of a classification. So if you look at set of all sequences, you may end up with three kinds of sequences. One, the one that I just now showed, these are called convergent sequences. Not this one, sorry. This, what I just now showed, is what is called divergent. Convergent sequences, the ones where limit exists and is, yeah, and we can show that if at all it exists, it is unique. The other one is this, where it eventually either goes to plus infinity or minus infinity. So this is not convergent, but every not convergent need not be divergent. So I'll say additionally, and limit uh, is either plus infinity or minus infinity. So now you may wonder, what is the third case? So not convergent need not be always of this type, either plus infinity or minus infinity. So this I'm going to uh, just tell you in a while. Can I go down? I should go to the next page. So consider f of n equal to, let's say, minus 1 power n times k. So put n equal to 1, you realize minus k. Put n equal to 2, you realize plus k, because minus 1 square is plus 1, so it's k. N equal to 3, you again go back to minus k. N equal to 4, you have even, so it is plus k. And so your sequence written as a set is simply minus k plus k minus k plus k and so on. And therefore, in the limit of minus 1 power n k as n tends to infinity is not definitive. So it's either k or minus k, k for an even, minus k if n odd, right? So uh, for even numbers, it is behaving in a certain way, that is, it's all positive k. For odd subscripts, it is behaving in this way. Therefore, we give a new name to this called oscillatory sequences. So now that the categorification is very clear, you set of all sequences either fall into the class of all convergent sequences or divergent sequences, or I'll change colors, oscillatory sequences. So Terry Tao actually begins with something else which is not standard. He he calls something called epsilon steady sequences. I will talk about it in my next video, but for today, I think this is enough. I've given examples of uh, convergent sequences. I've given examples of divergent sequences, and also I've given an example of an oscillatory sequence. But to really end on a nice ending, we should look at things, because the example I gave it convergent sequence is really trivial. So let's look at this. Xn equal to, let's say, 6 by n. So try to visualize this on a real line. Let's try to visualize it on the real line. Let's say this is 0, this is plus 1, minus 1, plus 2, minus 2, plus 3, minus 3, 4, 5, 6. I think let's make it as 4. So let me change my function as f of n equal to 4 by n, because my space is problem. So you see, if n equal to 1, let me put n equal to 1 implies x1 is just 4. I'm here. I'm here. N equal to 2 implies x2 is equal to 4 by 2, which is 2. I'll come here. N equal to 3, I'm I'm going to use this color as something. Uh, Please note what I'm thinking. So n equal to 3 implies x3 is 4 by 3, which is, if you take up a calculator, which is something like 1.333. So I'll still use this. Now n equal to 4, it is x4 is just 4 by 4, which is 1. I'll change colors now. It's 1. N equal to 5 implies x5 is 4 by 5. So now I'm either at 1 or less than 1. See? So it is something like 0.8. And so you are now coming uh, 1 or less than 1. So I'm not going to be precise now. Now they tend to get closer to 0 after a while. So how close? how close to zero we get. And what is the importance of this? Why did I really say zero? One obvious answer is because all your elements are positive. uh, I'm just saying that they have to be eventually, if they are coming, the numbers are less than one, they'll have to eventually go to zero. But more technically, what I want to say is limit of your, I'll now drop the function notation. I'll simply say limit of xn as n tends to infinity is limit of, what is my function? 4 by n as n tends to infinity, which is, see, as n tends to infinity, one knows that this limit is going to be zero. And that is why I said how close to zero. So we can set your epsilon and say for all n greater than some n naught. I mean, by the way, our parameterization is natural numbers. So there is some natural number n naught, after which, given a very small epsilon, something like 0.00000001, very small epsilon, can we say that all sequence elements, let's just imagine that is something like 10,000th number and beyond. After that, all sequence elements are going to fall in an epsilon ball. This is a very important thing. So I used pink to really state that eventually we are going to come in some epsilon ball. And in fact, as I said, it's all because uh, they're all positive. So though I'm saying an epsilon ball or an epsilon interval, I'm eventually in the positive portion of this epsilon ball. All your elements are going to be clustered around or inside the epsilon ball. And that is the technical definition of limit. Clustered around or around the limit, in the sense that all xn after for n greater than or equal to n naught will lie in the interval 0 epsilon. Okay, so we will make this more precise in the next class, and that's the technical definition one has to really look at in order to prove more theorems on this. So we shall end here. Let's end the discussion here. So yeah, I'm going to quickly look at another thing called boundedness also next time.